Welcome to the Deep Dive. Today we're taking a pretty big step, moving beyond just talking about large language models.
Yeah, we're wading into something critical now.
Right, into what feels like the biggest challenge for AI in business right now. Actually operationalizing autonomous agents.
Getting him out of the lab, basically.
Exactly. Moving from these, cool sandbox experiments to systems you can actually rely on day in, day out for core business stuff.
And this is really where things are heading, isn't it? The sources you sent over and a lot of industry forecasts, they're saying, what, by 2028?
Yeah, a significant majority, well over half, they predict, of complex Gen AI interactions will be handled by these agents.
That's a huge shift. It means AI stops being just a fancy chatbot and becomes this automated decision-making engine that handles multiple steps.
But that word agent gets thrown around a lot. It can mean anything from a simple script to, well, something much more complex. How are we defining autonomous AI agent for this deep dive? What makes it distinct?
Good question. For us, it's quite specific. An autonomous agent isn't just following orders. It needs to understand the intent behind the request.
Okay, understand the goal.
Right. Then it has to plan a sequence of actions to achieve that goal. Then, crucially, execute those actions independently, often using different tools or services.
And it doesn't just stop there.
No. And this is the key bit.
Yeah.
It has to adapt that plan on the fly. Based on what happens during execution, the feedback it gets, it needs to adjust. It's not just reading a script.
It's like it's writing the script as it goes.
Kind of, yeah. Playwright, director, actor, all rolled into one, making decisions moment by moment.
And that dynamic nature, that non-determinism, that's the source of its power, obviously.
Absolutely.
But it's also, as you pointed out from the sources, the root cause of why making these things operational is so darn complex.
That's the core tension. You've got systems designed for autonomy, for flexibility, but enterprises need predictability, control, reliability.
And bridging that gap is our mission today. You shared some great sources outlining really 3 critical pillars the industry is focusing on to solve this.
That's right. First, how do we make them reliable? That points to fine-tuning.
Okay, tuning the model itself.
Second, how do we ensure they're safe, governed, and ultimately trustworthy? That brings in rigorous evaluation.
Evaluation and governance.
And third, how do we make them actually integrate smoothly with everything else? Standardizing how they connect, using protocols like MCP, the Model Context Protocol.
Fine-tuning, evaluation, standardization.
Got it.
This deep dive is basically the shortcut to understanding how people are tackling these big operational hurdles right now.
Hopefully, yeah.
Okay, let's unpack this then, starting with that first fundamental piece. Making a general-purpose LLM actually fit for a specific job. Reliability through fine-tuning.
So these agentic systems, they're pretty clever in concept, right? They try to combine the best of both worlds.
You mean the general smarts of the LLM?
Exactly, that huge general-purpose brain with a specific toolkit. You know, the actual tools it needs to do a particular job, like accessing databases or APIs.
And the idea is they can handle really complex, multi-step problems that need both that general reasoning and specific actions.
That's the promise. But there's an immediate conflict baked in.
Which is?
The base LLM is a generalist. It's amazing. It can write a sonnet, summarize a research paper, generate Python code.
But it knows nothing about my company's specific way of doing things.
Precisely. It doesn't know your internal reporting structure, your compliance rules for financial transactions, the weird quirks of your custom-built CRM API. It has zero built-in knowledge of that specific domain.
So without that deep specific knowledge, the powerful LLM becomes, what? Clumsy.
Clumsy is a good word, or maybe just inappropriate. It might pick the right type of tool but use it in the wrong situation. Or it might mess up the parameters.
Or worse, do something that technically works but completely violates some internal policy or business logic it wasn't aware of.
We see that a lot in early tests. The agent follows a logical path, but it's a path that leads off a cliff from the business perspective because it lacked that specific grounding.
So fine-tuning. This is the strategy to inject that specific knowledge, like teaching the agent the house rules.
Exactly. You're essentially baking that domain-specific understanding directly into the model's weights, its core programming.
It's not just giving it a manual to read each time. It knows it.
Right. And the sources are clear. This isn't optional for serious applications. It's the strategic step you have to take to systematically boost performance and, crucially, reliability. You feed it specific annotated examples so it learns how, when, and why to use its tools according to your rules. Hashtag tag 1.2, analyzing system limitations addressed by fine-tuning.
Okay, the need for this becomes really obvious when we look at what happens without fine-tuning. The source has highlighted 3 big limitations, or maybe pain points. Let's start with token inefficiency.
Ah, yes. This is a huge practical problem. Because the base LLM knows nothing specific, you have to tell it everything in the prompt every single time you run the agent.
Everything. Like what?
The agent's persona, its goals, a detailed list of every single tool it can use, explanations of all their parameters, how to format the calls, maybe even step-by-step instructions for using a reasoning framework like React.
Wow. Okay, so if the agent has a lot of tools, that prompt could get massive. Tens of thousands of tokens.
Easily. And here's the kicker. Every LLM has a context window limit, right? A maximum number of tokens it can process at once.
Right, like 128K or 200K tokens, depending on the model.
So if you burn, say, 75% of that precious window, just setting the stage, defining the tools and rules, you've dramatically shrunk the space the agent has left for the actual work.
The problem solving, the reasoning, tracking its own
Yeah,
steps.
the critical thinking part is like the agent spends most of its effort just reading the instruction manual for the job rather than doing the job itself.
And that inefficiency, that huge prompt being processed every single time, leads straight to the second limitation: high execution costs.
Absolutely. Think about it. You're paying for every token processed.
Yeah.
If you have to feed this enormous setup prompt into the model for every single customer interaction, every single automation task,
Especially in high volume scenarios.
the compute costs skyrocket. It creates this massive operational drag.
And fine-tuning helps here
Because that knowledge, the tools, the rules, the parameters gets baked in. It's part of the model now. So the prompt for each execution can be much shorter, much more focused. Here's the user request. Go.
freeing up token space and cutting down compute costs.
Dramatically, often by factors of 5 or more, just by shrinking that initial prompt overhead.
Okay, efficiency cost. Now, the third limitation, the sources called this the gravest limitation: error propagation. This sounds serious.
It is. It's kind of the Achilles heel for these multi-step autonomous systems. An agent's task isn't usually one shot. It's a chain of decisions and actions.
Right. Step 1, gather info. Step 2, analyze. Step 3, execute action.
Exactly. Now imagine an agent doing, say, a complex financial transfer. If it makes a small mistake early on, maybe in step 1 it misunderstands a date format or picks the wrong database because 2 names look similar,
That initial small error.
it poisons the entire rest of the chain because the agent, acting autonomously, trusts its own previous steps. It builds subsequent decisions on that initial faulty premise.
Even if the later steps are logically sound based on the wrong info.
Precisely. It's following a logical path, but the starting point was flawed. So the agent's overall success rate just plummets. It can get stuck in loops, trying to fix a problem downstream that was actually caused way back at the beginning.
And fine-tuning attacks this directly.
Yes, because it aims to give the model that deep, domain-specific understanding needed to make the correct decision at each step, especially those critical early ones. It prevents the chain from breaking at the first link. Hashtag tag 1.3, Practical Guide to Data Collection for Fine-Tuning.
Okay, so if fine-tuning is the fix, we need the right medicine data. What kind of data do we actually need to collect? The sources seem to break it into 2 main types: teaching the tool mechanics and improving the overall reasoning.
That's a good way to put it. Let's start with the tool-specific data. This is about being really precise, almost surgically precise. We need to teach the model exactly when to use a specific tool.
The context.
Yes, how to call it, getting the parameters right, and critically, what to do with the output it gets back.
Let's unpack the when. If I have, say, 2 different search tools, one for internal docs and one for the public web, how does the training data help the agent choose?
You need to create examples that specifically highlight the difference in context. Scenario A, user asks about internal company policy X. Annotation. Must use search internal knowledge base because the answer requires policy adherence. Scenario B, user asks for creative ideas for Y. Annotation. Must use search external web because a broader external perspective is needed. The annotations have to explicitly call out the reason for the choice.
Okay, so clear disambiguation. Now, the how configuring parameters, this isn't just syntax, is it?
No, it's about the logic. If a tool needs, say, a location and a date range, the training data shouldn't just show examples of calls. It needs to show the reasoning that led to selecting those specific values for the subtask at hand.
Like showing the agent's thought process.
Exactly. Using something like a React framework annotation helps here. Thought. User asked for sales in London last quarter. Action. Call get sales data with parameters location London, period, Q3 2024. You're training the model on the goal of the call, not just the structure.
Makes sense. And then the output expectations. What does the agent do after the tool runs?
This is about making the agent critical, not just a blind executor. If a tool always returns a deterministic result, like a math calculation, fine, the agent can probably trust it.
But if it's pulling data from, say, unstructured text,
Then the training data needs to show the agent verifying or filtering or maybe even transforming that output before relying on it for the next step. You train it to ask, is this output reliable? Does it make sense? Does it need cleaning up? This stops bad data from flowing down the chain.
the sources also mentioned a special focus on right tools, tools that actually change things, modify data, execute code, send emails.
Ah, yes. These are inherently higher risk, aren't they? If the agent messes up a read operation, it's usually recoverable. If it messes up writing to a database or executing a script.
Catastrophe could ensue.
Right. So fine-tuning here is absolutely non-negotiable. You need to train the model on the full range of scenarios for these tools: successful runs, expected failures, edge cases. The annotations need to be incredibly detailed, focusing on preconditions, safety checks, and the model's reasoning before it takes the irreversible action. You force it to think carefully about the potential impact.
And this is especially true for custom proprietary tools the base LLM has never seen before.
Definitely. If you built your own internal tools, the only way the LLM will learn to use them correctly and safely is through this kind of specific, annotated fine-tuning data. ###B, improving reasoning, planning, and decision-making.
Okay, so that's tool mechanics. But fine-tuning isn't just about the hands. It's about the brain, right? Aligning the agent's decision-making with the organization's goals and policies. How do we train that?
This is where we leverage internal knowledge. Think about all those internal documents: compliance manuals, strategy papers, process guides, decision trees.
Stuff that usually sits on a shelf or a shared drive.
Exactly. Instead of just feeding them to the agent as context via RAG retrieval augmented generation, which is helpful but temporary.
You use them as training data for fine-tuning.
Yes. You structure this information and use it to train the model's core decision-making patterns. The goal is to make adherence to company policy the agent's default behavior, its instinct. When faced with a choice, its internal weighting should lean towards the path aligned with documented company procedures.
That sounds powerful, but maybe a bit abstract. How do you make that policy knowledge practical for the agent?
Through concrete examples, essentially case studies. You create realistic scenarios demonstrating how decisions are actually made in your organization. Show the agent. In situation X, policy Y was consulted, leading to decision Z, even though option W seemed plausible.
So it learns the application of the policy, not just the text of the rule.
Precisely. It moves from just knowing the rules to understanding the reasoning behind organizational choices. This is vital for improving its autonomous decision-making quality.
The sources also mention using execution traces. What are those?
These are basically the detailed logs generated by agents that are already running, maybe in testing or even limited production. They capture every step the agent took, its internal thoughts, if using a framework like React, the tools it called, the parameters it used, the results it got.
Like a flight recorder for the agent.
That's a great analogy. And the key step is human review and annotation of these traces. You look at a successful trace and label it as a good example. You look at a failed trace, identify why it failed, and annotate it as a failure mode with explanations.
Here's where you went wrong, and here's the policy you should have followed.
Exactly. You're providing direct feedback on the agent's reasoning path itself. This data is incredibly valuable for correcting those subtle flaws in logic that lead to error propagation.
And you can use this targeted data to train specialized agent components too, like a component that only validates data.
Absolutely. If you have an agent architecture with distinct roles, maybe a planner, an executor, a validator, you can create fine-tuning data sets specific to each role. Train the validator only on examples of data validation tasks, making it exceptionally good at that specific function, which improves the robustness of the whole system.
This sounds like it's not a one-and-done process. It feels very iterative.
It absolutely has to be. The environment changes, the tools get updated, users find new ways to interact, so you'll constantly encounter new failure modes, new ways the agent can break or behave unexpectedly.
So you need a process to capture those failures.
Yes, continuous collection, inspection, and analysis of production or near-production execution data is crucial. Identifying how and why the system fails becomes the primary source material for the next round of fine-tuning data.
Closing the loop.
Constantly. And the quality of the annotations you create for this new data is paramount.
You emphasized detail earlier.
Exhaustive detail. Using structured reasoning frameworks like React in the annotations really helps the model learn the process of thinking correctly, not just memorizing input-output pairs.
So the ultimate goal of all this effort, this meticulous data collection and iterative fine-tuning, what's the payoff?
The payoff is transforming the agent. It goes from being this interesting, maybe slightly flaky, novel solution into a genuinely trusted and reliable partner for that specific task. It becomes highly aligned with the challenges it needs to solve.
And you get those side benefits too.
Right. Because you've internalized the knowledge, you shrink the prompts, which cuts costs and boosts efficiency. Reliability breeds efficiency here.
Okay, so we've used fine-tuning to make the agent more reliable, more domain-aware, but just because it works well in the lab doesn't mean it's ready for prime time, right?
No.
The next big pillar is proving its readiness through evaluation and governance.
Exactly. This is where we directly confront that non-deterministic nature we talked about earlier.
How so?
Well, traditional software is mostly deterministic. You put in input A, you expect output B every single time. Testing is about verifying that predictable path.
Like checking if clicking save actually saves the file.
Right. But an AI agent, as we said, is more like that self-driving car. Faced with the same goal, get me home, it might take slightly different routes, call different tools, like checking traffic APIs, adjusting speed, based on real-time conditions.
Its internal decision path isn't fixed.
Correct. And because that path is dynamic, standard QA methods aren't enough. We can't just test one or two golden paths.
So evaluation becomes critical precisely because we can't predict every single sequence of actions it might take.
That's the crux of it. If you're deploying an agent for something important, like processing insurance claims, which involves multiple steps, verifying policy, assessing damage reports, checking for fraud flags, calculating payout.
Lots of potential paths and tool calls there.
Exactly. You need a rigorous process to ensure that all the probable paths, including the tricky edge cases and potential failure points, have been evaluated against clear safety, performance, and compliance standards before you let it loose on real claims. Hashtag tag 2.2 potential failure sources and risks, the what ifs.
Before we get to the how of evaluation, let's consider the what. What kinds of failures are we looking for beyond just the agent crashing? What are the risks?
Good point. We need to think broadly. One area is handling incomplete or ambiguous data. What's the agent supposed to do if a customer provides only half the required information?
It shouldn't just guess or freeze, presumably.
No, it needs a predefined, safe fallback. Maybe it asks clarifying questions, maybe it escalates to a human, but it must have a robust way to handle insufficient input gracefully.
What about behavioral issues? The sources mentioned information refusal.
Ah, yes. This touches on tonal integrity and preventing manipulative behavior. Imagine a customer support agent. If the customer refuses to provide, say, their email address, the AI agent absolutely must not become passive-aggressive or coercive.
Like saying, well, I can't help you then.
Exactly. Or anything sarcastic or mocking, oh, you don't want to provide the one thing I need. These behaviors, which can sometimes emerge unexpectedly from LLMs, have to be actively tested for and suppressed through governance roles and potentially more fine-tuning. The agent's tone needs to be consistently professional and helpful.
Okay, so data handling, tone.
Mm-hmm.
What about technical failures outside the agent's control?
That's the failed actions problem. The agent's internal logic might be perfect. It correctly figures out it needs to call an external API to check inventory. It forms the request correctly.
But the API server is down or the network times out.
Right. The agent needs sophisticated error handling for this. It shouldn't just crash. It needs to recognize the type of failure, network error versus API returning not found, log it appropriately, and maybe try again later or inform the user or try an alternative tool if one exists. It needs a plan B for external system failures. Hashtag tag 2.3, the 6-step structured evaluation process.
Okay, lots to watch out for. The sources laid out a pretty clear, structured approach to tackle this complexity. A 6-step evaluation process.
Yeah.
Step 1 seems foundational. Define metrics.
Absolutely. You can't evaluate effectively if you don't know what you're measuring. And you need a mix of metrics.
Like what?
Well, the basics.
Yeah.
Performance metrics like accuracy, did it get the right answer, latency, how fast was it, error rate, task completion rate, did it finish the job?
Standard stuff.
But then you need application-specific metrics. If it's supposed to call APIs, what's the successful API call ratio? And crucially, you need compliance and safety metrics.
Things like bias, fairness.
Yes, bias detection is key. Also, explainability. Can the agent justify its decisions? Source attribution. Does it correctly cite where its information came from? Things like a HP score hallucination, accuracy, performance are useful composite measures. Toxicity scores are vital for customer-facing agents.
And the sources emphasized adversarial robustness. Why is that so critical?
Because you're not just dealing with cooperative users. Adversarial robustness is about testing the agent's resilience against malicious inputs. People will try prompt injection attacks to make the agent say inappropriate things, reveal sensitive data, or bypass safety controls.
Jailbreaking, essentially.
Exactly.
Hmm.
You need specific tests that simulate these attacks to ensure the agent's guardrails are strong and its behavior remains predictable even when provoked. This is non-negotiable for production systems.
Okay, metrics defined. Step 2 is prepare data.
Right, you need test data that covers the scenarios identified by your metrics. This data should represent the full range of expected inputs, including common variations, edge cases, and those failure modes you anticipated.
And sometimes you need ground truth.
Yes, if your metrics require comparing the agent's output to a known correct answer, like for accuracy, you need that reference data, that ground truth, collected and validated beforehand.
Step 3, write code. This is where you actually implement the measurements.
Correct. You write the scripts or use evaluation frameworks to run the tests and calculate the metrics you defined. This often includes implementing the LLM as a judge technique.
Ah, yes. Using another LLM to grade the agent's work. Why is that necessary again? Seems a bit circular.
It seems circular, but it addresses the scale and subjectivity problem. For outputs where there isn't a single right answer, like judging the quality of a summary, the appropriateness of a tone, or the creativity of a plan, human evaluation is slow, expensive, and inconsistent.
And a separate, often larger LLM can do it faster.
Much faster and more consistently if you prompt it correctly. The key is writing very specific objective prompts for the judge LLM. Not, is this good, but does this response meet criteria A, B, and C, score 1-5. You treat the judge LLM like a configurable evaluation tool.
Okay, makes sense. Step 4, run the tests. Anything specific to focus on here?
Tool integration tests are vital. Does the agent actually connect to the database correctly? Can it parse the API response? Does the calendar scheduling tool work as expected? The agent's reasoning can be flawless, but if the tools don't integrate smoothly, the user experience collapses.
Then step 5, evaluate results and trade-offs. This sounds like the moment of truth.
It really is. You gather all the metric data, analyze it, and see how the agent stacks up. This is where you often have to make tough decisions. Like maybe the agent is super accurate, but it's too slow. Or it's really fast, but makes too many minor errors. You have to decide which metrics are most important for this specific application and where you're willing to make compromises. Do you optimize for speed or for accuracy first? This phase drives the optimization strategy.
Which leads directly to step 6. Optimize and iterate.
Exactly. Based on the evaluation results and the trade-off decisions, you go back and fix things. Debug the tool connection issues, refine the agent's workflow to improve the prioritized metrics, maybe tweak the prompts used by the agent or even the judge LLM, and then you run the evaluation again, hashtag tag 2.4, the iterative cycle. And importantly, this isn't a one-off cycle you do just before launch, because you can never test every possible real-world scenario up front.
You have to keep evaluating.
Continuous monitoring and evaluation in production are critical. You need to capture how the agent is performing with real users, identify any new failure modes that emerge, and feed that data back into the whole process.
So the data loop we talked about for fine-tuning applies here too. Production data feeds improvement.
Absolutely. It's a constant cycle of evaluation, learning, and refinement. It's the only way to build and maintain a truly robust and trustworthy agent over time. The real world becomes part of your ongoing test harness.
Okay, we've got reliability through fine-tuning, trust through evaluation. Now, security, especially when these agents aren't working alone, they often need to collaborate, right?
Yeah.
Passing a task from one agent or service to another.
Yes, these multi-hop flows are becoming very common. A user talks to a chatbot,
Which might call a router agent.
which then delegates to a specialist agent for customer lookup, which might then call another agent for billing updates.
It's a chain reaction. And this creates a big security headache.
A huge one, specifically around identity. How does that final agent, the one updating the billing system, know that the request originated from a legitimate, authenticated user with the permission to update billing?
And not from some rogue component inserted somewhere in that chain.
Exactly. How do you securely pass the user's identity and permissions along that potentially long and dynamic chain of agents and services? Hashtag tag 3.2, reviewing traditional identity delegation patterns.
Let's quickly touch on why the old ways don't quite cut it here. Pattern 1, no delegation at all.
Simplest case. The application connecting to the backend, say a database, uses its own service credentials. The database only knows the application ID, not the original user. Works for basic things, but zero user-level auditing or permissions.
Okay. Pattern 2, trusted assertion.
A step up. The application still uses its own credentials, but it asserts who the user is, maybe by sending a header, like a SAML assertion. The backend trusts the application's assertion and checks permissions based on that claimed user.
The trust is between the app and the backend, manageable for 2 hops.
Right. Pattern 3, simple delegation. Passing the user's token along. Here, the application gets the user's access token, which encodes their permissions, and just forwards it directly to the backend. The backend validates the user's token directly. Again, it works okay in simple point-to-point scenarios.
Yeah.
Hashtag 3.3 limitations and modern challenges.
But these break down quickly in our multi-hop agent world. Challenge 1, impersonation risk.
This is the big one. In that chain, user-chatbot, chatbot, router, agent A, agent B, how does agent B trust the identity it receives? It only sees the request coming from agent A.
It can't see the original user authentication way back at the start.
Exactly. So what stops a malicious actor, let's call them bad agent, from compromising or bypassing agent A and sending a request to agent B pretending to be a legitimate user? Agent B has no way to verify the original source of the identity claim if it's just being passed along hop by hop. The chain of trust is broken.
The sources mention the on behalf of OBO flow as a partial solution. How does that work?
OBO is a specific OAuth flow. The user authenticates to agent A. Agent A then takes the user's token and exchanges it with the identity provider, IDP, for a new limited scope token that allows agent A to call agent B on behalf of the user.
So the user explicitly delegates permission to agent A for that specific task.
Right. It works well for a single delegation step, agent A to agent B.
But that immediately hits challenge 2, transitive trust.
Yes, OBO works for one hop, but what about agent B needing to call agent C? The user might trust agent A, but they can't possibly know about, let alone explicitly trust, every single agent, BCD, that might be involved dynamically down the line.
The user needs to trust the system as a whole, not each individual component.
Precisely. OBO doesn't scale well for transitive trust in long dynamic chains. Managing all those delegated tokens becomes incredibly complex and hard to secure.
And the final hurdle, challenge 3, multiple identity providers.
This happens when the agent flow crosses organizational boundaries. Maybe your internal agent needs to call an external partner's API. Now you have 2 different companies, 2 different IDPs, 2 separate trust domains.
How do you securely pass and validate identity across those boundaries?
Traditional delegation patterns really struggle here. You need a more formalized, standardized way to bridge those trust domains. Hashtag 3.4 strategic solutions for agentic flows.
Okay, if the old ways fail, what are the modern strategies to handle identity securely in these complex, multi-hop, potentially cross-organization flows?
Strategy A is the foundation. Strict adherence to standards. Everything should be built on robust, well-understood protocols like OAuth 2.0 and OpenID Connect, OIDC. No custom security schemes.
Table stakes, really.
Absolutely. But the key mechanism, strategy B, is token exchange. This becomes the trust anchor in the multi-hop scenario.
Instead of just passing the original token along.
You exchange it at every single hop.
How does that work, and why does it solve the trust problem?
Okay, so user authenticates, gets token 1, sends it to agent A. Agent A doesn't just forward token 1. It takes token 1 to the central AP and says, "Hi, I'm agent A calling on behalf of the user in token 1. I need to call agent B. Please give me a new token specifically for that."
So the IDP is involved at every step.
Critically involved. The IDP does 2 things. 1, it validates token 1. Is the user still valid? Do they have permissions? 2, it authenticates agent A. Is this a known trusted component allowed to request this exchange?
Okay.
If both checks pass, the IDP issues a new token, token 2. This token is granted to agent A, but it's specifically intended for agent B. Agent A then sends token 2 to agent B.
And agent B validates token 2 with the IDP?
Yes. Agent B takes token 2, presents it back to the IDP for validation. The IDP confirms, "Yes, I issued this token recently to agent A for the purpose of calling you agent B." The trust is reestablished cryptographically at every hop, directly with the central authority.
That completely blocks the bad agent scenario, doesn't it? Because the IDP wouldn't issue a token to an unknown or unauthorized requester.
Exactly. It ensures the request genuinely came from the expected previous hop and is going to the expected next hop. It's the only robust way to maintain integrity through the chain.
Now, strategy C, contextual scoping. This is about limiting permissions along the way.
Yes, the principle of least privilege applied dynamically. When the IDP issues token 2 from A to B, the permissions or scope in that token should be only what agent B needs, not the full permissions agent A might have had.
So if agent A could read logs and write to the database, but agent B only needs to read logs.
Token 2 should only contain the read.log scope. Permissions are progressively narrowed as the token moves through the flow.
And how do you ensure token 2 is only used by agent B?
That's the audience claim. When the IDP issues token 2, it sets the audience claim specifically to identify agent B. When agent B receives token 2, its first check is the audience claim for this token actually me? If the token was intended for agent Z, agent B rejects it. This prevents tokens from being stolen and replayed against the wrong service.
Scope limits what the token can do. Audience limits who can use it.
Perfect summary. And finally, strategy D, centralization via API gateways. This sounds like making it manageable. It is. Implementing token exchange correctly at every single agent is a complex and error-prone. A much better architecture is to have all inter-agent communication go through a central API gateway.
And the gateway handles the tricky security stuff.
Exactly. The gateway can manage the entire token exchange protocol, validating incoming tokens, talking to the IDP, minting new tokens, ensuring correct scoping and audience. It centralizes the security policy enforcement and frees up the individual agent developers to focus on business logic, not complex security protocols.
Okay, reliability solved, security handled. The final piece of the operational puzzle is integration. How do these agents actually connect to all the external data sources and tools they need?
Right now, it's often a mess.
How so?
Well, if your agent needs to talk to 5 different systems, your CRM, a billing API, maybe a knowledge base, a ticketing system, a file share.
You end up writing 5 separate pieces of custom code.
Exactly. 5 bespoke adapters, what the sources brilliantly called that hand-rolled JSON glue code, each one tailored to the specific quirks of that one API.
And that sounds incredibly brittle.
It is. Every time one of those back-end APIs changes even slightly, its specific adapter code in the agent breaks. You have to manually update it, retest, redeploy. It makes scaling or adding new tools incredibly slow and painful.
So we need a standard way for agents to plug into things.
Precisely. And that's the problem the Model Context Protocol, or MCP, aims to solve. It was introduced by Anthropic, late 2024?
Yeah, relatively new, but gaining traction.
It's an open standard designed specifically to standardize how AI agents consume context, basically, data, and utilize tools, functions, or actions from external sources.
I love the metaphor used in the sources.
Yeah.
MCP is like the USB-C port for AI agents.
It's a great analogy. Your laptop, the AI agent, needs to connect to all sorts of peripherals, external services like databases, APIs, file systems. USB-C provides that single, standardized connector.
Monitors, hard drives, power, they all use the same port.
Right. MCP aims to do the same for AI. Instead of the agent needing a custom adapter for every single service, services expose their capabilities via the standardized MCP interface. The agent learns to speak MCP once and can then connect to any MCP-enabled service, #tag 4.2, the MCP architecture and primitives.
So what does this MCP world look like architecturally?
There are 3 main components. You have the MCP host, which is typically the AI agent itself.
Okay, the central application.
Then you have MCP clients running within the host, initiating connections for specific needs. And you have MCP servers, which are the external services exposing their capabilities via MCP. They usually talk using JSON RPC 2.0 sessions.
And what can these MCP servers actually do for the agent? What are the main use cases?
MCP standardizes methods for 2 core things. Context provisioning, that's fetching external data, like documents, database records, schemas, and tool utilization executing actions, like running a web search, performing a calculation, or calling another services function.
How does an MCP server tell the agent what it offers? The sources mentioned 3 primitives.
Right. These are the standard ways servers advertise their capabilities. First, there are tools.
Like API functions.
Exactly. Discrete, callable actions. Think create calendar event, get weather forecast, look up customer bide. The server declares the tool's name, provides a natural language description so the LLM understands its purpose, and gives a precise schema for the inputs and outputs.
So the agent knows exactly how to call it. What's the second primitive?
Resources. These are primarily read-only data elements the server provides. It might be the content of a file, or maybe just the schema of a database table.
Why just the schema sometimes?
It allows the agent to understand what data is available, for example, which columns exist in a table, before trying to construct a complex query to fetch the actual data. It's about providing structural
Oh,
awareness.
smart. And the third, primitive.
Prompt templates. These are predefined text templates provided by the server.
Why would the external service provide a prompt template?
It allows the service to guide or constrain the agent's behavior when interacting with it. For instance, a customer support MCP server might offer a template for generating an apology email, ensuring the agent uses the approved corporate phrasing and tone. It's a way for the service to enforce certain interaction patterns, expected at 4.3 MCP versus traditional APIs. REST.
Okay, tools, resources, prompt templates. That's how MCP servers expose things. But how is this fundamentally different from just interacting with a standard REST API? Lots of APIs have documentation and schemas.
The absolute game changer, the critical difference, is dynamic discovery.
Meaning,
With a traditional REST API, the client application, the agent in our case, is usually hard-coded against a specific API definition. The developer reads the static documentation, writes code to call specific endpoints, expects specific responses.
and if the API adds a new feature, a new endpoint.
The agent developer has to manually learn about it, update the agent's code, test it, and redeploy the agent. There's a significant lag in manual effort.
How does MCP change that?
With MCP, the agent can query the MCP server at runtime to discover its capabilities. It can send a standard MCP command, like tools list, and the server responds with a machine-readable catalog of all the tools, resources, and templates it currently offers.
So if the team behind the billing service adds a new MCP tool 5 minutes ago,
The agent can connect, ask what tools do you have, see the new tool on the list, understand its schema, and potentially start using it immediately without any code changes or redeployment on the agent side. It makes the whole system incredibly adaptive.
wow, okay, that is a big difference. Dynamic adaptation versus static coding.
Huge. And the other key aspect is standardization.
You mentioned this with the USB-C analogy.
Right. If you have 5 different services, traditionally you need 5 different REST API adapters in your agent. With MCP, even if you have 5 different MCT servers for GitHub, Slack, billing, etc., the agent uses the exact same standardized MCP calls to interact with all of them.
Like tool call.
Exactly. The agent learns the standard MCP tools call format once. Then, whether it's calling the create a repo tool on the GitHub MCP server or the send message tool on the Slack MCP server, the structure of the agent's request follows the same MCP standard. It's develop once, integrate many times.
But wait, if the underlying service is a traditional REST API, like GitHub's, how does MCP talk to it? MCP isn't replacing REST, is it?
No, absolutely not. MCP isn't a competitor to existing APIs. Think of it as a specialized layer built on top of them. The MCP server often acts as a wrapper.
A rep.
Yes. The GitHub MCP server, for example, receives a standardized MCP tools call request from the agent, like create a new repository with this name. The MCP server's job is then to translate that high-level standardized MCP request into the specific, potentially complex proprietary REST API call that the actual GitHub service understands. It handles the mapping, authentication, maybe JSON formatting nuances.
So MCP provides this AI-friendly, standardized, dynamically discoverable interface. And the MCP server does the dirty work of translating that into whatever the back-end system actually speaks.
That's exactly it. It makes integrating agents with diverse systems, file systems, internal databases, external SaaS tools, payment gateways vastly more efficient and scalable.
Okay, let's make this concrete. The theory sounds great, but how does MCP actually help in practice? Use case 1 from the sources, automating stuff on GitHub.
Right. So imagine you have a dedicated GitHub MCP server. This server wraps the standard GitHub REST API, exposing common actions as MCP tools.
Like creating issues, reviewing code?
Exactly. An AI agent connects to this GitHub MCP server. Because of dynamic discovery, it sees tools like review pull request, analyze code changes, check coding standards, prioritize issues, scan dependencies.
So the agent can then automate routine developer tasks.
Precisely. It could automatically review pull requests for common style errors or potential bugs, freeing up human reviewers for deeper logic checks. It could analyze incoming code changes to detect patterns associated with past bugs. It could enforce consistent coding standards across all commits.
What about managing issues?
It could automatically sort, tag, and prioritize incoming bug reports or feature requests based on predefined rules exposed via the MCP server, maybe even calling external security scanning tools presented as MCP resources.
The business impact seems clear. reducing the drudgery for developers.
Absolutely. It cuts down on time spent on repetitive tasks and wrestling with that hand-rolled JSON glue code for custom integrations. Developers can focus more on creative, high-value programming. You'd expect to see faster development cycles, higher code quality, and cleaner code bases.
Okay, second use case, customer support. This often involves juggling lots of different systems, doesn't it?
Totally. A support agent might need to look up customer details in the CRM, check billing history in the finance system, examine server logs for technical errors, consult the internal knowledge base for solutions, and update the ticket in the support platform.
That's the classic swivel chair problem, looking at 5 different screens.
It's slow, inefficient, and prone to errors. Each system has its own interface, its own login.
How does MCP help here?
You create MCP servers, wrappers, for each of those backend systems: CRM, billing, logs, knowledge-based ticketing. A single AI agent then connects via MCP to all of them.
Using standardized calls.
Right. The agent's internal logic for get customer billing history is the same MCP call structure, regardless of whether the billing data lives in System A or System B, as long as both expose it via an MCP server.
Let's run through the example from the sources.
Yeah.
Customer reports a failed login, says their subscription expired even though they just paid.
Okay. The AI agent connected via MCP takes a report. It uses an MCP tool call to the CRM MCP server to identify the customer account based on their username or email.
Step 2.
It calls the billing MCP server's check payment status tool, passing the account ID. It confirms a recent payment.
Step 3.
Maybe it quickly checks the logs MCP servers get Loginer's resource to verify the specific error code the user encountered.
What's 4?
Finding the payment confirmed but the account still expired, it calls the subscription management MCP server's reactivate subscription tool.
All automatically using standard MCP interactions.
Exactly. Then it formulates a response to the customer. I've confirmed your recent payment and reactivated your subscription. Please try logging in again. This whole sequence, which might take a human navigating multiple systems several minutes, could happen in seconds.
The benefits seem massive. Faster response times, 24/7 availability.
Significant reduction in manual effort for the support team, fewer errors because the process is consistent, and much easier scalability. Adding a new backend system just means creating a new MCP wrapper for it. The agent itself doesn't need a major rewrite. #tag 5.3 final synthesis. So when you look at these use cases, the strategic consequence of something like MCP becomes really clear.
It's more than just a technical standard.
Much more. It's potentially a game changer for how we build applications using LLMs. It standardizes the messy, complex integration part, allowing AI agents to move from being these isolated, often fragile, custom-built solutions towards being truly robust, efficient, scalable components within a modern enterprise architecture.
It replaces all that brittle, bespoke integration logic.
With a universal adapter, specifically designed for AI interaction, it's a foundational piece for making autonomous AI truly operational at scale. #tag outro.
Wow, okay. That was a really comprehensive deep dive. We've journeyed through the core requirements for actually getting these autonomous AI agents out of the lab and into reliable production.
We covered the 3 essential pillars, didn't we? First, building that core reliability through focused fine-tuning, really getting that domain knowledge baked in to combat things like error propagation.
Right, making them fit for purpose. Second, establishing trust through that rigorous 6-step evaluation process and strong governance, including testing for adversarial robustness, making sure they're safe and behave predictably.
Definitely. And third, ensuring they can actually connect and scale securely through standardization, using token exchange as that critical trust anchor for identity in multi-hop flows, and adopting protocols like MCP as the universal language for integration.
Looking back across all those sources, the common theme that jumps out is this relentless drive for control and predictability in systems that are inherently non-deterministic.
That's a great way to put it. Whether it's controlling the model's knowledge through data, controlling its behavior through evaluation and governance, or controlling its access and interactions through identity and integration standards, it's all about achieving reliability and trustworthiness despite the autonomy.
We've really seen how this combination of techniques, fine-tuning, governance, protocols like MCP is what transforms agentic AI from this exciting but maybe slightly scary new technology
Into something that can become a verifiable, trusted, and highly efficient component of enterprise architecture.
So we'll leave you, our listeners, with a final thought to chew on. We've talked a lot today about that hand-rolled JSON glue code, the custom, often fragile logic built over years to connect disparate systems. Considering the potential of standardized AI-friendly integration layers like MCP, take a moment to think. What parts of your own work or your organization's processes are currently bogged down by that kind of bespoke, brittle integration? And what could the impact be on efficiency, on costs, on innovation if you could standardize those interactions, potentially leveraging an AI layer to manage the complexity? Something to consider.